Welcome to this explainer. When you look out the window of a commercial jet, you see a massive turbine engine. But what you don't see is the hyper-intelligent digital nervous system running the entire show behind the scenes. We're going to dissect that incredible electronic brain today. So, how exactly does a massive turbine engine know how much thrust to safely produce without, well, literally ripping itself apart? Let's dive into this fascinating question. Because jet engines operate at extreme temperatures and just unimaginable RPMs, human reflexes simply aren't fast enough to manage the fuel flow and air valves directly. We need a computerized middleman. And that middleman is the FADEC. Now, the FADEC is the overarching system, but its core component is the EEC, the electronic engine control. Think of the EEC as the actual dual-channel computer acting as the brain's two hemispheres. What's absolutely crucial to understand here is the full authority part of FADEC. This means there are no mechanical backups whatsoever. The computer has total 100% control over the engine. If the digital system fails, you can't just pull a physical cable to pump fuel. The computer is the engine's sole lifeline. Here is how we're going to break this all down today. First, we'll meet the engine's brain. Second, check out its hardware and senses. Third, explore the dual-channel architecture. Fourth, look at control modes and logic. Fifth, dive into built-in fault protection. And finally, number 6, memory and identity. All right, section 1, meet the engine's brain. You might think this critical piece of hardware sits safely inside the climate-controlled cockpit with the pilots, right? Actually, no. It's right out there in the elements. Inside this rugged metal housing are two separate computers, Channel A and Channel B. It literally bolts onto the outside of the engine's fan case, constantly communicating with components like the fuel metering unit, which is mounted right on the front face of the fuel pump. Now, because it's a highly sensitive computer bolted to a violently vibrating jet engine, it needs some serious protection. It relies on shock mounts to absorb all that intense shaking and convection cooling to keep its internal processors from melting down. Plus, to guarantee it never loses power, even if the main aircraft's electrical system completely fails, it has its own dedicated permanent magnet alternator, or PMA, which is driven directly by the engine's gearbox. It literally generates its own life support. Moving on to section 2, hardware and senses. Just like a biological brain, the EEC needs a nervous system to sense its environment and muscles to take action. An isolated computer is completely useless unless it can communicate with the massive machine it's attached to. To make maintenance flawless, the aviation industry uses an incredibly specific color coding system for the wiring. Imagine popping the hood of a jet engine. Seeing a blue wire instantly tells the mechanic it's feeding data directly to the Channel A computer, while a yellow wire is strictly for temperature sensors. It's just a beautiful visual failsafe against human error. So, the EEC constantly reads inputs from its senses. This includes air data computers to know altitude and speed, precise position feedback from rotary and linear variable differential transformers, and temperature data. For example, there's a specific fuel temperature sensor thermocouple attached right to the fuel outlet line on the rear of the fuel oil cooler. Once it processes all that, it commands its muscles, using torque motors and solenoid drivers, to physically open and close valves within the fuel metering unit, adjusting the exact spray of fuel based on what the pilot is asking for. Let's look at section 3, the dual-channel architecture. Like we said earlier, when you have a computer with full authority, you absolutely cannot afford a blue screen of death mid-flight. Total reliability is ensured through redundancy. The EEC relies on two completely identical independent channels operating simultaneously. But here's the kicker. Only one, the active channel, is actually driving the engine at any given time. The standby channel is just sitting there doing all the same math in the background, verifying the inputs. And here is a really fascinating detail. Every single time the engine is started, the channels actually alternate who gets to be in command. This ensures both halves of the brain stay fully exercised and ready to go. Next up, Section 4, Control Modes and Logic. So how does this brain actually decide how much fuel to pump into the combustion chamber? Well, it operates on some very specific pre-programmed logic to establish what we call closed-loop control. The engine always prefers the highly precise normal mode, which uses EPR, or engine pressure ratio. But it's designed with strict fail-safe characteristics. If the pressure sensors required to calculate EPR suddenly fail, the FADEC doesn't just throw its hands up and give up. It automatically drops into an alternate mode, substituting N1, which is the physical speed of the engine's massive front fan blades, to safely keep the thrust flowing. Section 5. Built-in fault protection. Let's think about a wild scenario for a second. What happens if a sensor completely fails in flight? How do the two channels handle missing information without panicking? Well, thanks to the cross-channel data link, if channel A goes blind on one sensor, channel B will instantly share its homework, so the active channel can keep flying the plane. The data literally crosstalks through an internal mating connector. If the primary channel's data is lost entirely, it just borrows the synthesized data from the secondary channel. This step-by-step logic is just pure genius. The built-in test equipment, or byte, is constantly relentlessly checking for errors. If it finds one, it assigns a numerical weight to that specific failure. A minor sensor failure gets a low weight, a critical valve failure gets a high weight. Then, the two hemispheres literally weigh their own health against each other. The healthiest channel, the one with the lowest overall fault weight, automatically wins control. It is a completely autonomous survival mechanism. Finally, Section 6, Memory and Identity. For our final section, let's look at how a blank slate computer knows exactly what specific engine it is bolted to. Because you might have a dozen identical EEC boxes sitting in a maintenance hangar, but the actual engines they attach to could have totally different thrust ratings. It comes down to this brilliant little device, the programming plug. Notice how it's attached directly to the engine fan case with a permanent lanyard, and it plugs right into the EEC housing. This plug is the actual identity of the engine, storing all the non-volatile memory schedules for that specific configuration. Because this plug dictates the exact power output and limits, say, telling the computer whether it's allowed to produce 22,000 pounds of thrust or 26,000 pounds, you can swap out a broken brain box for a brand new one, but the plug's identity must always stay tied to the physical engine hardware. The new computer simply reads the old plug and instantly knows who it is. As a final layer of fail-safe protection, the FADEC won't even attempt its maximum precision EPR mode if it can't verify its own identity via that plug. If a mechanic accidentally forgets to connect it, the FADEC immediately forces the system into the safer alternate N1 mode. Interestingly though, if the plug accidentally disconnects while already in flight, the system smartly ignores the disconnect to prevent a sudden loss of established power. So, with the FADEC fully automating thrust, tracking faults, and seamlessly switching brain hemispheres in midair, are we looking at a traditional engine or basically a flying supercomputer? I hope this explainer has transformed how you view the mechanical miracles hanging off the wings of modern aircraft. The next time you hear a jet engine spool up, remember, you aren't just hearing burning fuel and spinning metal. You're hearing a fully automated, self-diagnosing, dual-channel supercomputer executing millions of calculations a second, constantly weighing its own health to keep you safely in the sky. It truly is a marvel of engineering.